Hello, this video is about simple harmonic motion. So basically, a simple example of simple harmonic motion would be something that dangles off a string, and if it's displaced a little bit, it goes backwards and forwards like that through a small angle theta. So you can see here we've got a piece of, well, you could take it to be a rod of length L. Um, so a rod of length L with a mass at the end, and that mass has a weight mg. I've written it there, but that's just for the purposes of doing a little bit of trigonometry to work out certain variables. Now, I've called this arc through which the mass swings S. So, using a bit of basic standard trigonometry, you can work out that S is equal to L sine theta. So, if you resolved this length L vertically, you'd have L cos theta, and that would be equal to that radial vector there, or you could call it the height. Um, of course, if you resolve L horizontally like this, that's 90 minus theta there. So we'll just so that's 90 minus theta. This is L. So up here we would have L cos 90 minus theta. Right? L cos 90 minus theta, which is equal to L sine theta. Right? L sine theta. Well, we're not so bothered about the roof, if you like, from which or the beam from which the mass is suspended. But we do know that by symmetry, for small angular values theta, that we can approximate that to be S. So S is equal to L sine theta because that's a Z angle. And L sine theta is therefore equal to S for relatively small angles of theta. But we can go further than that because, as I said, we've got S equal to L sine theta along here. Again, when sine theta, or rather when theta is small, so we could write as theta tends to 0. So for small theta, sine theta is equal to theta. So like if you find the sine of angle 0.05 degrees, you will get something that's very close to 0.05 degrees. So therefore we can assume that S is equal to L theta around along here or around here. I mean these two, this arc and this distance S, this horizontal distance S, are so close together they're more or less equal. So it's all about taking limits and using mathematical analysis to determine that. And of course, when you've got S equals L theta, we'll call this equation 1. You can differentiate it twice. Now, I've differentiated with respect to time, t, because this is swinging. This mass, we'll call it, well, we know that the mass is m, and it's exerting a force downwards here, which is mg, if you can see that. Now, so if you differentiate this with respect to t, you get s dot is equal to L theta dot. And of course you can differentiate this now again to get s double dot equal to L theta double dot. And this is the same as writing d squared s by dt squared equal to L theta double dot. But we want an equation which is basically of this form, where the theta in the second derivative is the same as a theta on the right hand side of that simple harmonic motion equation. And we're going to show how to get to that from here. So we know that we've got S equals L theta double dot. Now, using a bit more trigonometry on this triangle of forces, if you like, we know that that is, well, I'm going to try and just make this look a little bit neater, because I don't think that's very clear, actually. We've got a component. So if we just take this, so we've got mg coming down here like this, vertically down, and we know that that is angle theta, right? And this is 90 minus theta, sorry, 90. I don't think that's wonderfully clear, so let's just redraw it again. So we've got theta 90 minus theta there, and we've got mg. Now, in terms of S, the force acting along here, which is the same as talking about this S here, so the force acting along S, you could do it with that horizontal line. We know that that force, which is centre seeking, so the force is acting in this direction, so it's minus ms double dot. Let's just separate that. So we've got F equals ms double dot. But we know from this triangle of forces here that if we extend this line, that's 90 minus theta there, and that is theta, by just simple trigonometry and geometrical arguments surrounding these angles. So there we've got mg. Along this line, that will be mg cos theta, and along here, this is going to be the force is going to be mg sine theta. Right, so along here, we've got, well, again, I'll just explain that once more. In the direction in which L is pointing, that would be mg cos theta, and in this direction, along the arc of the circle that is being produced along S, we've got mg cos 90 minus theta, right? So we'll just rewrite this and eventually we'll get it. So we've got mg cos 90 minus theta. But that, of course, can be written more simply as F equals mg sine theta. You know, if you do A-level mathematics, high school level mathematics, you should know quite well that cos 90 minus theta is the same as sine theta, and as theta tends to 0, we've got F equals mg theta. Now that force F is exactly the same as that force F there, minus ms double dot. So what you can see is I've equated mg theta to minus ms double dot. Okay? And if I just erase this and make it a bit clearer what I'm actually doing. Again, we want to get this equation only in terms of theta or theta double dot. We want to get it in terms of theta double dot and theta. Well, we know that s double dot up here is L theta double dot. S double dot, or d squared s by dt squared, is equal to L theta double dot. That theta double dot would also be d squared theta by dt squared. So we can substitute into the s double dot this component here, L theta double dot. And I'm going to write it as d squared theta by dt squared. So that's minus m L theta double dot. And so we get this equation here. Now, we'll notice that m cancels on both sides. And this equation can be rewritten as d theta by dt squared right equal to, well, if we divide both sides by L, we've got minus, or rather if we divide both sides by minus L, we've got minus G over L theta. Now this is a constant of proportionality. You can also work this equation out for things like ice pucks on springs and things, and springs going up and down vertically or even horizontally. It's the same sort of principles, and usually whatever is written here, in this case it's minus G over L. It might be something different if you were modelling an ice puck or a horizontal spring or a vertical spring oscillating, you know, in some kind of plane or whatever. Then you might have a different constant there, but it doesn't really matter, because what we say is that we write k equals, in fact we'll call it k squared equals minus G over L. So we don't include the minus sign in the constant bit. We call k squared equal to G over L. So if we rewrite this out, we have d squared theta by dt squared equal to minus k squared theta. Right, now for those of you who are doing high school mathematics or have done it, you'll be familiar with that simple harmonic motion equation. And that basically states that the second derivative of theta with respect to time, so it's like talking about the acceleration of theta with respect to time, is proportional to the angle theta, where k squared, or minus k squared in this case, is the constant of proportionality. Now that basically brings us up here to what I've already written down prior to commencing the video. Again, d squared theta by dt squared equal to minus k squared theta. And again, if you're familiar with high school mathematics and beyond, you'll know that a solution to this equation, which I've called star, is a cos kt plus b sine kt. And why k and not k squared? Well, theta is actually equal to a cos the square root of k squared t plus b sine, that's not very clear, is it? My writing's terrible. Sine square root of k squared t, and of course the square root of a squared term is just the term on its own. In that case, the square root of k squared is just k in both cases. Now, you have to find the constants by, you will normally be given some initial conditions, like for example, theta is 90 degrees at t equals 0, because presumably you would start this mass swinging from this point here, and it would come down here. So theta would be 90 degrees in that case. Or you might write pi over 2. We could do this example. We might leave that to a later date. And then, of course, you would have to differentiate this for the velocity or the rate of change of theta with respect to time, and then you'd have some value for your velocity, like 0 when t equals, I don't know, if it takes 1 second to get from there to there, then theta would be 0 at t equals 1 second or something like that. And by doing so, by doing both of those things, you can work out what the constants a and b are. But I wanted to go on to explain how you would solve a simple harmonic motion equation like the following. I'll just erase that. Okay. So what about something like d squared theta by dt squared minus 10 plus 5 theta equal to 0. And this will be modelled from some kind of physical situation like this, but one in which there's in this case, an added constant term that falls out of the modelling of whatever it is you've got, and can then be written down in the form of an equation like this. And in this case, that constant would be 10. Or on this side of the equation, minus 10. But anyway, that doesn't really matter too much at this stage. So how are we going to solve an equation like this? And I'll give you some initial conditions, so we can revert back to this in a moment. But the initial conditions are theta equals 0. No, sorry, theta equals 90 degrees. We'll call it pi over 2. Let me just erase that. So theta equals pi over 2 radians at t equals 0, and theta equals 0 radians, that means radians, but it's seldom used, at t equals 1 second. Okay, so those are our initial conditions, and we've got to solve this equation and substitute those into the solution that we get, so that we can get the particular solution. So, well, how do we deal with this? This isn't in that form, but we can put it in that form. So we've got d squared theta over dt squared. Now we've got a minus 10 here, but we can see that we can take that 5 theta to the other side of the equation, just like it is there. And we get minus 5 theta. Okay, well, that's similar to what we've got there. But we've got a minus 10 here, and we don't have anything up there. So how are we going to kind of get rid of this minus 10? Well, we don't really get rid of it. We kind of absorb it into a new equation, which we're going to form as follows. So if we add 10 to both sides, so that we eliminate the minus 10 rather, from the left-hand side and end up with plus 10 on the right-hand side, we have an equation which still looks like that, but isn't quite. So what we can do is we can write d squared theta by dt squared, and that is equal to, well, what I'm going to do is I'm going to kind of factorize this and write it as a product of a theta plus something and multiply it by something else. Well, you can see that a common term on the right hand side here is 5, because 10 is 2 times 5. So we can take a 5, actually we can take a minus 5 out of this expression on the right hand side. So we've got minus 5 theta. Now we've got to be careful here, because if we take a minus 5 out, leaving us with a 2 at this side, we've got to bear in mind that that must be minus 2, okay? Because if we multiply out this bracket with the minus 5, just as a check that we've got the right expression there, we can see that we've got minus 5 times theta, which is minus 5 theta, plus, because a minus times a minus is a plus, 5 times 2 is 10. So we know that that is the correct equivalent expression of the line there. Now, is that looking more like what we want? Well, we've got a theta here, we've still got a minus 2. And we know the 5 must be k squared. But how are we going to get this exactly like that? Well, if we let u equals theta minus 2, right? U equals theta minus 2, then we can work out that du by dt is equal to d theta minus 2 by dt on that side of the equation. Well, what is the derivative with respect to t of theta minus 2? Well, minus 2 is just a constant. If you differentiate a constant, you get 0. And that turns out to be d theta by dt. Now, let me just erase this part of the board. In fact, we've dealt with that, so hopefully if you're taking notes, Um, you'll be able to see where we've gone with that. And of course, you can always play back the tape, the video. So we've got du by dt. Let's make that look more like a u. I'm afraid you have to excuse my handwriting sometimes. So you've got du by dt equals d theta by dt. So straight away we can see that if we differentiate both sides of this again, we get d squared u by dt squared equal to d squared theta by dt squared. And of course, that's exactly the same as writing d squared theta by dt squared equal to d squared u by dt squared. Okie doke. So we substitute d squared u by dt. We substitute d squared u by dt squared in for d squared theta by dt squared, and we substitute u in for theta minus 2. So what we have is d squared u by dt squared equal to minus 5 u. And there you can see we've got that in that form. That is a reductionist form of that, but in terms of now a different variable. So straight away we can write down the general solution. So the general solution is u. Let's you might not be able to see it there if I'm in the way, so we'll just write it here. U equals a cos, it's going to be the square root of 5 times t plus b sine the square root of 5t. Okay, but we need to rewrite it back in terms of theta. Well, we know, let me write this in a different colour. We know that u equals theta minus 2. So we substitute theta minus 2 back in for u. So let me get a green pen. Therefore, theta minus 2 equals a cos root of 5t plus b sine root of 5t. Okay, so we can just add 2 to both sides of this equation now, and I hope you can see that. So we get theta equals 2 plus a cos root of 5t plus b sine root of 5t. Okay, let's just get rid of that little black line there. Okay, just separate that out. There we are. Now we're nearly home and dry, because all we have to do is substitute in the initial conditions, and I might have to just get my calculator, which is somewhere. I can't remember where I put it now, but basically we've got theta equals this expression here, and let's just erase the right hand side of this board. Okay, So what did I say the initial conditions are? I think I chose initial conditions to be theta equals pi over 2 at t equals 0 and theta equals 0 at t equals 1 second, didn't I? Okay, so we've got 0, so, well, we've got theta equals 2 plus a cos root 5t. So I'm rewriting it up here. Plus b sine root 5t there. Now, we know that theta is pi over 2 when t is 0. So let me write this in red now. So we've got pi over 2 on this side. That's equals 2 plus a cos 0. Let's put that in brackets. Plus b sine 0. It's actually root 5 times 0, but it comes out to be 0. Right? So we've got root 5 times 0 there, root 5 times 0 there. So it's both 0 there and 0 there. That simplifies to give pi over 2 equals 2 plus a, because the cos of 0 is 1 and the sine of 0 is just 0. So from this, we can see that a equals pi over 2 minus 2. And I'm actually going to write it as pi over 2 minus 4. Is that right? So I'm just, yeah, that looks okay. So that's a. That's our a value, our constant a. Now, we found that straight away. Sometimes it's not as easy as that, but it is when at least the t is 0 in at least one case. Now, to find b, right. To find b, we need to differentiate this once with respect to time. So, d theta by dt is equal to, well, the 2 disappears, and here we've got, let me see, a root 5, and in fact it's negative because cos differentiates to give minus sine root 5t, and then we've got plus b root 5 cos root 5t, right? Now we know that d theta by dt, I call that theta dot up there for the initial condition. It was a slip up of mine right at the very beginning. Yeah, we need, for the initial conditions, we need a value for theta at some time, which in this case is 0, and then we need a value for theta dot at some other value of t other than 0, which in this case is 1. So that's where I did slip up there, so many apologies. Now, we know that theta dot is 0, so it's just 0 there, and that's equal to minus a root 5 sine root 5 plus b root 5 cos root 5, because t is just 1. Now, in actual fact, this before we do anything else, before we start calculating any values, we can actually get rid of the root 5s. We know what A is. So we've got A, 0 equals A. So we've got pi minus 4 over 2 sine root 5 plus B cos root 5. And I'm actually going to work it out in terms of the tangent. So if we bring this to the left hand side, this bit here, we can actually write that as B cos root 5 is equal to, well, I'm going to switch these around because I end up with a minus sign otherwise. So we've got 4 minus pi over 2 sine root 5. Okay, and of course we can work out quite easily that B. Let's just move the camera down a little bit because that sometimes gets a little bit out of focus. Oh, there we are. So B is equal to 4 minus pi over 2 sine root 5 over cos root 5. And that's just the same as writing 4 minus pi over 2, all in brackets, times the tangent of root 5. So if I get my calculator over here, I don't think B is going to work out exact. So we find, if I just erase this, right. So we find that B, which we know is 4 minus pi over 2 times tan root 5. Well, we've got to work out what tangent of root 5 is. So let me see, we've got a third there, and we want it in radians. Right. Tangent, where's root 5? And tan of root 5 in radians is equal to minus 1.27456 to 5 decimal places. Right? So B, and in fact we could actually work this out. I'm just wondering if there's an easier way of writing tan of root 5. I don't think there is. So basically, if we multiply minus 1.274556459 by what we've got in the brackets, 4 minus pi divided by 2, then we find that B, and do check this, make sure that I haven't made any mistakes, B is minus 0.55 to 2 decimal places. Right? So, what we've actually got is the final particular solution, the final particular solution is therefore theta equals 2 plus pi minus 4 over 2 cos root of 5t, and if I just erase this part of the board so we've got a bit more room, I don't have to write anything under anything here. So we've got plus b, well it's negative is b, minus 0.55 sine root 5t. And that is the answer to the question. So is the particular solution to d squared theta by dt squared minus, I think I said minus 10, didn't I? Plus 5 theta equals 0. So I hope that you've enjoyed that and that you've got something out of it, and that it's helped you perhaps in this area if that's where you were looking for help within. And until the next video, I'll bid you farewell and see you soon. Okay, bye.